Hello everyone. Today we are going to study about modeling of first order differential equations. Okay. Now altogether we have 9 to 10 uh, of the problems where we want to find out how does this differential equation of the system looks like, and how does the solution of them looks like. Okay. So let's start with the population growth problems. And the population growth problems are like in this way. Suppose that Pt is a number of individuals in the population of human, insect, or anything having the constant birth rate beta and death rate delta. Then during a short time period interval delta t, approximately beta Pt delta t births happened and delta Pt delta t death happens. Then our change in population at a particular instant of time given by dp by dt, instantaneous change or instantaneous rate of change of population per unit time, is given by beta minus delta pt delta t. Okay, we can consider this whole thing to be a constant, so our differential equation looks like this. So this is our population growth problem, where our differential equation looks like this. Now, where this k is a proportionality constant and it is equal to beta minus delta, where beta is the number of births per unit time, whereas the delta is the number of deaths per unit time. Now, similar to this, there is something called decay problem. Okay, and that decay differential equation, which involves the same differential equation but a minus sign in front of the k. That means if we have a decay problem, then our differential equation looks like d. Let's suppose this to be p, for instance, is equals to minus of k pt. Okay, so this is called the decay problem. This is called the population growth problem. And this is called the decay problem. Now, the nature of the solutions. Let's try to find out the nature of the solution of this kind of differential equation. As you can see, the rate of change of population is depending upon or directly proportional to the population at a particular instant of time. Such kind of relation is only possible when we have a exponential function. That's why if you try to find out the solution of this, you would get an exponential solution. So we have got dp by dy equals k times p. Let's suppose this should be, for instance. So we have, so now we can see we have variables. We can separate the variables here. So dp by p equals k times dt. If you integrate both sides, you would get ln of p is equals to k t plus integrating constant. If you take this and if you know the relationship in between the logarithm and exponential, you would be familiar with this. Then I can write this EC as a singular constant. This is the solution of the graph problem. If you consider the differential equation is the decay problem, then it would be minus, and that would give us minus kt, and that would be the solution of a decay differential equation or a decay problem. If you want to see it visually, then it is trivial, but if you want to see this in graph, then the population, if it's a growth equation, it looks something like this, and if it's actually, it might go from somewhere here because we have an initial population now. So initial population is V0 and it increases as the time increases. If it's a decay problem, then it's a population, it's the initial population, and it will decrease over time and approach to the zero over time. This is something that the solution should look like. Okay, now let's go to another kind of problems, which is called the compound interest problems. So modeling a compound interest problem. Let's suppose we have ST be the amount of money in a saving account at time t in years, and suppose that the interest compounded continuously at an annual interest rate r. Okay, now continuous compounding means that during a short time interval, the amount of interest added to the account is approximately delta S is equals to R times ST delta T. So that our differential equation would look like ds by dt is equal to Rs, where R is actually representing the rate of compounding interest. Okay, now at particular instant of time, the amount of interest being added is given by this. So this is our differential equation, which account for modeling of compound interest problems. Let's see some other problems of modeling, and then only we will go to the actual solving the problems. Now another category of problems would be temperature problems. So let's suppose T denote the temperature of a body, and let Tm denote the temperature of the surrounding. Okay, so let's suppose we have T will be the temperature of the body, and Tm with the temperature of surrounding. If that's the case, at any time t, then the time rate of change of the temperature of the body, that means dt by t, dt by dt is given by minus of k t minus tm, and this is called the Newton's law of cooling differential equations. Okay, this differential equation also called as a Newton's cooling equation, which follows Newton's law of cooling. This is our differential equation. Let's try to find out the solution of these differential equation. So Tm, yeah. So Let's try to find out the solution. If we say this, let's multiply minus kt inside the bracket. That will give us minus kt minus plus ktm. Okay. Now this tm and k. Tm is the temperature of the surrounding and T is the temperature of a body. Now temperature of the surrounding is constant or is assumed to be constant, and we consider that over time the body is either heating or cooling such that the temperature of the body is changing. So we can think of it as a linear differential equation if it's in first order. If you know that, then we can consider this in this form. This is our differential equation, or to be precise, linear differential equation of first order. Now this equation has a very definite solution, which has its own standard way of finding the solution. Now we have a solution of such differential equation is y times integrating factor is equals to integration of integrating factor times q, which is this function which is on the right hand side of the equation, times dt or any other variables which is differentiating it. So what is y? Y is just the solution, but in our case the solution is t and integrating factor. Now integrating factor can be found out easily by considering e to the power kt, actually just k dt. This is going to give us e kt, and this is e kt equals to integration of e kt times what is q? K times t m dt. K being a constant, come out of this integration sign, and we have already assumed that the temperature of the surrounding is also constant, so this will also come out. If you know, it would be just ktm. The integration of this would be by k ekt plus c. K and k would be cancelled, so we'll get t ekt, and this can be written as t minus tm is equals to c ekt. Okay, or we can say temperature of a body at any instant of time t. I think it is not visible here. Up to now this is visible, right? Okay, then t, temperature at any instant of time t, is given by Tm, which is the surrounding temperature, plus C EKT. This is the solution. Okay. Now one thing that I think I have, yes, I think one thing that I missed here is that if I see this differential equation, it says that at every instant of time t, after a certain point tm, it is increasing. But since I have taken this k to be minus k, That means the body is not heating but rather cooling. Our system should have given a solution which looks where the solution would look like this, that is decreasing over time. It is because I had done a mistake, because when I divide it by exponential of kt, there would have been a minus sign there. As a result, our nature and our nature of the solution as well as the assumption would be a proper case, proper use. Okay, so this is how the modeling temperature problems is done. Now, one of the most important differential equations in physics are falling body problems. Now let's try to find a differential equation hold account for the falling body problems, as well as let's try to find out the solutions of those. What do you mean by falling body problems? If you are in Earth and not in any other hypothetical world, the one thing that is going to influence your falling body the most is the gravity. Suppose we have a body at height h, and it falls from that. Then what is the driving force for that? The driving force is obviously the gravity, or we can say the weight of the body, right? Weight of the body, which is m into z, is actually a force which is pulling it towards the ground. Now, this gravity is a type of acceleration. That means it's change in velocity over time. Now, because of the weight, the body falls. We can think of it with a body is falling, but there is air resistance. Air resistance, let's suppose that to be K times V, that is opposing that pulling force due to gravity. Is there something else that is so what we're essentially doing here is we are trying to find out the forces that act on the body. First one, we said that yes, the weight of itself is a force that is acting on this body, and second, I said the air resistance also exert a force on the body. Now what else is there to talk about? So I think this is it. These are the things. Then it says that the net force on the body is given by the net force. The net force on the body is given by the weight minus, because the weight is pulling the body towards this direction, towards the ground, and the air resistance is in the opposite direction a bit. So we have to put a minus sign in front of it. So this is the net force that our body is facing. Our body is being exerted. on the body. So it's m dv by dt minus k v equals force. Now force is what? mz. So m times dv by dt. Actually, I think I did a mistake here, because even though the body is, I mean, yeah, we can say that. Now, in physics, we try to assume the gravity and acceleration different. We suppose that gravity is pulling it towards with some force, so the weight is there, but because of the air resistance, the acceleration of the body is not equal to the pulling gravitational force or gravitational weight. That's why we consider acceleration to be different as well as the gravitation to be different. So actually, I should have said that in this, so here the force and the acceleration due to, and the force due to acceleration are actually different things. So nevertheless, we have got a equation which looks like this. I'm sorry for this. It's actually mz, and the acceleration is actually m dv by dt minus kv. This is our differential equation, which hold account for the body falling under the influence of gravity in the presence of air resistance. If there was no air resistance, this term won't be here. So let's divide m on both sides. We'll get dv by dt equals g minus k by m v. This is our differential equation. If we take this thing over here, this will be our differential equation. Now, one thing that you should consider is the convention of gravity. Some people have an interest in putting a minus sign since the body is falling towards the gravity. That means that suppose the positive gravity only if someone is throwing body against the gravity. But some people are crazy enough to think that when the body falls, then that is the positive gravity, and when the body is thrown upward against the gravity, then that is a minus z. So everyone has their own convention to understand it. You can use either of this, but to be consistent with the book, I assume this to be minus z. Okay, wait a second. No, plus z. Sorry. So plus z, always remember that plus z is when body is being pulled towards the gravity. So let's find out the solution of this. Now if you see it, again we have a first order linear differential equation. So here we can compare it with dy by dt plus ptt equals qt. This is our ordinary first order linear differential equation. So comparing it, now the integrating factor is given by this. If you want to find out the integrating factor of this, that would be integration of p, that is k by m into dt. That's gonna be e k by m times t. Now solution is y times if is equals to integration of q times if, which is integrating factor, dt. Y is our v times if is e k by m, t is equals to integration q, that is g if, that is e k by m t dt. This g is a constant. We can take g as a constant outside of this integration sign. If we integrate it, it will be this, and if I divide it by this thing, it will be this. So our solution look like v equal mg by k plus ce minus k by m t. Velocity any instant of time is given by weight per unit k, that means the weight times the frictional force, plus c is any constant, e to the power minus k by m t. Okay, so this is the solution of it. Let's go to very important modeling problem, which is called mixing problems. Mixing problems has very many applications in various fields, and it is also important from the perspective of our examination. Suppose a situation. A tank is being filled with the salty water, which is sometimes called as a brine, and another brine with salt concentration CIN flows in at rate RIN 8 times T. So it says that suppose a tank is there, a tank is filling water, or we can say brine solution. Okay, so it's a brine solution, brine, or we can say the salt solution. Now there is a situation where further brine is coming into the tank at concentration Cin at the rate RIN, that is Rin, at any time t. Well stirred brine with salt concentration C out flows out at rate R out. So that means it's a mixture. Okay, we have a mixing system here. Inside this tank, we have a mixture, and it rotates to mix the solution, and we have got another concentration. So that means the concentration in and concentration out are different. So C out at R out now Qt denote the amount of mass of salt in the tank at any time t. Suppose in here Qt represents the amount of salt. That means the dissolved salt in the water in the solution be defined by Qt, and Vt with the amount of brine in the tank at any time t. Then it says that the change in the amount of salt is given by change in amount of salt at any particular instant of time, interval of time, is given by C in R in delta T minus C out R out delta T. Now at a particular instantaneous time, that would be C in R in minus C out R out. This is an ordinary differential equation where C in means the concentration coming in, C out is the concentration coming out, and R is the rate in and R is the rate out. The rate at which coordinate time the brine solution is being taken out, okay, or is being flowing out or in of the tank. So now if you see this R out, what do you mean by R out? That is a rate of flow. Rate of flow of what? Salt, right? So rate of now R out can be written as just R out, okay? R out can be also written as the amount of salt which is completely dissolved in this per unit volume of the solution. That is the rate, because we know that the concentration is actually equal to amount of solute by amount of solvent. So we can think of this rate as a concentration. If you do so, then we can write this equation is dq by dt equals C in R in minus C out times qt by Vt. This becomes a solution. This becomes a differential equation. Okay, this becomes a differential equation. Sometimes question asks us to find out the rate of change of volume inside the tank. In that case, we just take rates, not the concentrations. Wait a second. Sorry, I said concentration, but I took the rate. Actually, it's wrong. When I'm talking about concentration, okay, concentration is this. That means we have R out here. Yeah, sorry for that. So this is concentration. Now, sometimes if we have been asked to find out the volume inside the tank at a particular instant of time, then it's given by rate in by minus rate out. This is another differential equation. Now we can think of this differential equation as a mass conservation equation and this to be a volume conservation equation. If you try to find out the solution of this, it's pretty simple. And let's do that. So we have this differential equation. Now dq by dt, so we can think of it dq by dt. Let's take this, yep, I think this one, yeah. This becomes plus R out by Vt times Qt into, or sorry, is equals to what? C in R in, right? Now just to be clear and just to not to be get ambiguous about these things, let's suppose this to be K equals R out by Vt and C in R in to be maybe what? Beta? What do you think I should call it? Yeah, let's suppose this to be beta. If I say so, then I would get dq by dt plus k times q is equal to beta. Now this is a first order linear ordinary differential equation. So we have got this. Now we have got a solution of this. For that we need to find the integrating factor. Integrating factor is this. So our solution would be this. If I divide it, solution is q equals beta by k plus this. If I substitute the real values of beta and k, I will get beta is equals to Cn R in by k is R out by Bt plus C e to the power minus R out Vt e to the power this times t. Okay, this is our solution. If you want to model radiocarbon dating or carbon dating, then it has a differential equation which is very trivial. We have already seen such kind of differential equation. Actually, the carbon dating is very familiar and very similar to the decay equation problems. So we have dQt by dt, where the Qt is the amount of radioactive substance, and this is again proportional to the amount of solution at a particular instant of time, and this suggests us that we will get an exponential solution. Okay, so this is it. This is our radio carbon dating problem equation. Now we have pretty important problem involved in population dynamics. And in population dynamics, we have seen one kind of problem which is called unrestricted. So we have already seen exponential growth rate, which was actually minus for radioactive, and if it is plus, then this differential equation, if Qt represents the population at time t, then this equation will hold account for the population growth, exponential population growth. But let's suppose the population growth is not exponential. Let's suppose it grows, but after a certain period of time, it comes to a halt. Something like a sigmoid function. Now this sigmoid function or sigmoid kind of population is described by something called logistic equation. And logistic equation says that logistic growth equation, which says that unlike the unrestricted growth, there is a carrying capacity K that the population size cannot exceed. So that means for positive R, there are two equilibrium at yt equals 0 and at yt equals k. Okay, that means our differential equation looks like this for the logistic equation. Suppose we have a logistic equation where y represents the population at particular instant of time, r is the rate of increase of population, then it is this equation which is called logistic growth equation. If you see this, yes, so this is the thing. Okay, now one thing that you can see here is r times y minus r y squared by k. That means it's a non-linear but first order differential equation. Now when we have a non-linear kind of first order differential equation, we have our own way to find the solutions of them. That means we can't use the integrating factor method to find the solution. Alright, now this is the logistic growth equation. Now there is something called logistic growth model with a threshold, and in that we have 1 minus y by t of y. That means y by t of y. Yes, and if this means that if the population size is below a certain threshold level, then the population will decrease to 0. But if the population is above a threshold, then it will behave like a logistic growth. Okay, let's suppose this means if you want to see it this way, so let's suppose this is a 0 and this is a threshold. Now if its population is below this threshold, then it will go eventually to the 0. But if it's above the 0, then it will increase and go up to a certain threshold, is suggested by the logistic growth equation. Okay, this is all about it. These are the things that we will study in this logistic equation. Sorry, mathematical what? Mathematical modeling problems. Okay.